So, how do we analyze the structure of something so incredibly small that a human hair looks like a giant redwood tree next to it? Well, today we are zeroing in on X-ray diffraction, or XRD, specifically how we apply it to nanoparticles. Look, whether you're engineering targeted drug delivery systems or maybe cooking up hyper-efficient solar panels, XRD is your go-to. It's fast, it's reliable, and totally non-destructive. It literally lets us see exactly what's happening down at the atomic level.
But let's pause for a second. How do we actually measure the physical structure of something completely invisible to the human eye? I mean, when a particle is measured in nanometers, literally a billionth of a meter, you can't just toss it under a standard microscope and call it a day. We need a proxy. We need something with a wavelength tiny enough to interact with the actual atomic lattice of the material itself. And right there, that's exactly where X-rays enter the chat.
So here's our roadmap for today. We'll start with the core principle, then peek inside the XRD machine itself. After that, we'll decode some nanoparticle patterns, dive into the math behind size and strain, and finally, we'll wrap up with the limitations of XRD.
All right, part 1, the core principle, X-rays and atomic planes. To really get a handle on this non-destructive technique, we have to think about how light interacts with crystal structures. Imagine incident X-rays coming in at a very specific angle, bouncing right off the periodic atomic planes of a crystal. Think of these planes as our interrogators. When the X-rays hit the atoms, they scatter, right? And if the conditions are absolutely perfect, the scattered waves align flawlessly, crest to crest. We call this constructive interference, or diffraction. It creates this highly magnified signal, but we can actually physically measure.
And that brings us to the absolutely crucial part, Bragg's law. This equation defines the precise condition for that constructive interference to actually happen. You know the one. N lambda equals 2d sine theta. Here, lambda is our X-ray wavelength, d is the interplanar spacing between the atoms, and theta is our angle of incidence. When this whole geometric equation balances out perfectly, boom, we get a completely unique diffraction pattern. It's essentially a mathematical lock and key for atomic spacing.
Moving right along to part 2, inside the XRD machine, powder XRD instrumentation.
Okay, so how do we take Bragg's law out of the textbook and actually put it on a lab bench? Well, we can break this physical process down into 3 really elegant steps. First up, our X-ray source, which, by the way, usually uses a copper K-alpha target, fires a beam directly at our sample. In this case, we're talking about a polycrystalline powder sitting on a rotating mount, which we call a goniometer. Step 2, as the angle shifts, those scattered X-rays periodically satisfy Bragg's condition. And finally, step 3, a detector swings around, captures those diffracted rays, and records the signal intensity against the angle. And we typically plot that angle as 2 theta.
Next up, part 3, decoding nanoparticle patterns, reading the clues.
So now we're transitioning from the actual physical machine to the digital output. And let me tell you, that unique diffraction fingerprint is an absolute goldmine of information. First and foremost, we get phase identification. We literally take the peak positions on our graph and cross-reference them with these massive standard reference databases, like ICDD or JCPDS. That tells us exactly what crystal structure we're dealing with. But it definitely doesn't stop there. We can also assess the degree of crystallinity. Just by looking at peak sharpness, we can estimate the crystallite-size, and we can even detect microstrain and lattice defects hidden within the structure. Pretty amazing, right?
Now, there's a really stark contrast to keep in mind here between bulk materials and nanoparticles. If you test a large, perfect bulk crystal, your graph is going to show these incredibly sharp, intense, needle-like peaks. But nanoparticles, they uniquely show broader, way less intense peaks. And the reason is simple. Because the particle is so unimaginably small, there just aren't enough atomic planes to perfectly cancel out that slightly off-angle scattering. So that peak broadening isn't a mistake or bad data. It's actually a vital clue about the nanoparticle's true dimensions.
All right, part 4, math, size, and strain. Specifically, the Scherrer equation and Williamson-Hall.
So, to figure out exactly why those nanoparticle peaks get so fuzzy and what that fuzziness actually means, enter the Scherrer's equation. This is just a remarkably powerful formula. It lets us estimate the average coherent crystallite size directly from that peak broadening we were just talking about. It essentially mathematically correlates the width of the peak to the physical diameter of the crystallite itself. The basic rule of thumb, as crystallite size decreases, peak broadening increases.
Let's quickly look at the players in this equation. Big D is your target. That's the mean crystallite size. Then you've got your shape constant, K, which usually sits right around 0.9, and your known X-ray wavelength, lambda. But honestly, the real star of the show here is beta. Beta isn't just a random symbol. It represents the actual physical width, specifically the full width at half maximum, or FHWM, of that broadened peak. By measuring that physical width and plugging in your Bragg angle, theta, you can accurately calculate the size of your nanoparticle domains.
But of course there's a catch, right? What happens when that peak broadening isn't just coming from the tiny size of the crystallite? What if the crystal lattice is stressed or warped, or maybe it's just full of defects? Well, that structural microstrain also causes the peaks to widen. So if you just blindly use the Scherrer equation, you might actually incorrectly assume your particles are way smaller than they really are. And this is exactly where we need the Williamson-Hall analysis to step in, to neatly separate the size broadening from the strain broadening.
This brings us to the Williamson-Hall approach, which is just a truly elegant piece of linear algebra. Check this out. By plotting beta cosine theta on the y-axis against 4 sine theta on the x-axis, we generate a linear graph. And the beautiful part? The mathematical slope of that line directly gives you the microstrain epsilon. Meanwhile, where that line intercepts the y-axis, the intercept, well, that gives you the exact parameters you need to calculate the true crystallite size. It just perfectly untangles those two overlapping effects.
And that brings us to our final section, Part 5, Limitations of XRD, the Boundary Conditions. Now, as amazing as all this math and machinery is, no scientific technique is completely perfect. XRD definitely has its constraints. First off, it really struggles with ultra-small sizes. We're talking anything below 3 to 5 nanometers. At that point, the peaks just kind of merge with the background noise and vanish completely. Second, remember that it measures the coherent domain, meaning the continuous crystal lattice. So, if several crystals clump together in an agglomerated particle, XRD only sees the individual crystalline puzzle pieces, not the whole clump. Furthermore, it just can't accurately quantify amorphous or non-crystalline content all on its own. And finally, you always have to correct for instrumental broadening, simply because the machine itself inherently blurs the data just a tiny bit.
Which leads us with a pretty fascinating final thought for this explainer. XRD is an absolute heavy hitter when it comes to crystal structure, phase composition, and crystallite size, for sure. But to truly grasp the complete, holistic picture of your nanoparticles, especially if they're heavily agglomerated or partially amorphous, how are you going to combine XRD with other techniques? How will you use complementary tools like transmission electron microscopy or maybe Raman spectroscopy to finish solving the nanoscale puzzle? Well, you've got the framework now. It's up to you to crack the case. Thanks for joining me.